Today we're going to learn about the LDR instruction in assembly language. We'll break it down in step by step with a fun and simple analogy. By the end of this video, you'll have a clear understanding of how LDR works and how we use it to access memory efficiently. Let's get started. Before we dive in, let's quickly recap what we learned about the arrays in our previous lesson. Then meet Bob, our helpful guide for today. He's here to make learning LDR instruction easy and fun. Let's get started. In our previous lectures, we learned about how to declare an array. When you run this instruction, it allocates 4 bytes of memory for the array named numbers in the RAM and fills it with the values 10, 20, 30 and 40. Once the array is created in the memory, the first address, in our case the address of 10, is known as the base address of the memory. Remember this, we'll be using this notation throughout this course. Please keep it in mind. Now let me introduce you to Bob. This is Bob, who works for a postal service, and today Bob is here to help us understand the LDR instruction and its different types. Let's take a look at a typical day in Bob's life. Bob starts his day by turning on his computer. He notices a new notification. When he opens the notification, he sees a request to pick up a package from a specific location. Without wasting any time, Bob quickly writes down the address on a piece of paper and heads to that location. Once he reaches that location, he picks up the package. Once he picks up that package, he returns to the office for further processing. Sounds simple, right? Now let's look at how this relates to our LDR instruction. Take a look at this program. From the previous slide, we know that an array was created and its base address is 200. When you execute this first line of code, it copies the base address, which is 200, into the register X1. This is just like Bob writing down the address on a piece of paper. X1 now holds the location of the array in the memory. Next, when you run the second instruction, it loads the value 10 into the register X0. This is similar to Bob traveling to the house, picking up the package and bringing it back to the office. Think of X1 as Bob's piece of paper. It doesn't store the package itself, but holds the address where the package is located. The square brackets in the next instruction indicate that X1 holds an address. When you execute that command, it tells the processor 3 things. Go to the memory location stored in X1, retrieve the value from that address and store it in X0. That's how the LDR instruction works. Now Bob has a new assignment, but this time things are a little different. Instead of giving him an address, we simply tell him to go to the previous address and pick up the package from the house next door. Luckily, Bob already has the original address written on a piece of paper. And even better, all the house numbers in that street are sequential. So all Bob has to do is increase the house number by 1, and just like that, he has the new address 201. Now that he has the new address, Bob goes to that new location 201, picks up the package. Once again, we have our array in the memory. When you execute the first instruction, you copy the base address 200 in register X1. In the previous example, X1 initially pointed to the memory location where 10 is stored, the address 200. Now we need to make it to point to the next value, which is 20. And lucky for us, 20 is right next door. Its address is 201. How do we convert 200 to 201? Easy, just add 1 to it. Just like Bob updated the address on his paper, we update our registry by incrementing its value by 1. Now X1 points to 201. We can use the next instruction to load the value 20 in the register X0. We can also achieve this same thing using pre-indexing. Instead of manually adding 1 to the address, there's an instruction that does everything for us in one step. Let's see how it works. First, we use the first instruction to get the base address of array, which is 200. Next, instead of updating X1 manually, we use pre-indexing that does two things at once. it increments the value 200 to 201. Then it loads the value 20 in register X0. This means Bob doesn't even have to write the updated address on a piece of paper. He gets the new address and the package in one go. But what if you wanted to skip one house and go 2 doors down instead? What if you wanted to get 30 instead of 20? Simple. In pre-indexing, you just change the number of spaces you want to move. Instead of adding 1, we replace it with 2. Now the instruction will automatically increment x1 by 2, fetch the value 30 and store it in x0. That's all about pre-indexing. It allows us to move through the memory efficiently, just like Bob going to the next house over and heading straight to the right package. Now it's a brand new day. Suddenly, he gets a new notification. When Bob opens it, he sees that this time he has 2 packages to pick up instead of just 1. So what does he do first? Just like before, he writes down the address of the first location on a piece of paper. He goes to the first location and picks up the first package, just like he always does. But remember, today is different. He still has 1 more package to pick up. Now that Bob picked up the first package, he looks at his paper and updates the address. This is exactly how post-indexing works. Just like Bob, we first get the base address using the first instruction. When we execute the second instruction, the processor does 2 things in order, just like Bob. First, it looks at the address in x1, goes to that location in that memory, and fetches the value 10, store it in x0. Then, it updates x1 by incrementing the address, just like Bob updating his paper with the new address 202. Remember, Bob first picks up the package from the first house before updating the address. Similarly, the processor first copies the value from the memory before modifying the register. That's how post-indexing works. Instead of updating the address first, like pre-indexing, here we fetch the value first and update the address next. Now let's compare the values in the registers after using pre-indexing and post-indexing. In pre-indexing, the address updates first, then the value is loaded. So the value stored in x0 is 30 and the final value in x1 is 202. In post-indexing, the value is loaded first and then the address is updated. So x0 holds 10 and x1 holds 202. That's the key difference. In pre-indexing, we update the address first and then load the value. In post-indexing, we load the value first and then update the. Understanding this helps us navigate the memory efficiently in assembly language programming. Thank you everyone. See you in the next lecture. Bye-bye.